Okay. Let's prove that n cubed is 6n choose 3 plus 6n choose 2 plus n. So let's say we have a room with n people. We want to choose 3 of them to be the president, vice president, and treasurer. So this is a weird group of people, so it's okay if one person holds more than one role. So for instance, one person can be both the president and the vice president. So how many ways can we do this, right? Well, on the one hand, there's n choices for the president, n choices for the vice president, and n choices for the treasurer. So because one person can hold any number of roles, it's just the number of ways to choose the committee is just n cubed. So our governing body. So well, let's see how else we might count this, right? So if everyone holds a different role, so if every role is held by a different person, then we can choose our 3 people, class officers, in n choose 3 ways. Then there are 3 factorial ways to permute them. So for instance, if I chose Alice, Bob, and Carol, then there's 3 ways we can assign Alice, Bob, and Carol to the president, vice president, and treasury slots. If there are only 2, so that's 6n choose 3. If there are only 2 people taking on the 3 roles, then, well, first we can choose which 2 people in n choose 2 ways. Then we can pick which of the 2, so which role, which of the 2 roles are shared by one person. So, another way to think about this is which role is the one that only one person has. So let's say one person is treasurer and another person is the president and the vice president at the same time. Then well, once we've chosen our 2 people, there are 2 ways to assign which person takes 2 roles and which person takes 1 role. So times 2. So that's 6n choose 2. If all 3 people get the same role, then there's just n, or if all 3 roles are held by the same person, then there's just n ways to choose which person does all 3 jobs. So we've proven that n cubed is n plus 6n choose 2 plus 6n choose 3. And this is a perfectly valid argument. We don't have to do any algebra in this proof, and this is a perfectly valid proof. If we want, we could even check this for a few examples and interpolate. So 1 cubed is 1 plus 6 1 choose 2 plus 6 1 choose 3. Well, there are 0 ways. What is 1 choose 2, right? There are 0 ways to pick 2 people from 1 people. So that's 0. Similarly, there are 0 ways to pick 3 people from 1 people. So that's also 0. So this holds for n equals 1. When n equals 2, this says 2 cubed is 2 plus 6 times 2. 2 is 2 plus 6 times 2 choose 3. So this is 1, and this is 0. So this is 8 is 2 plus 6, which is true. Yeah, so we could keep checking, but we've proven it. like checking just as a check, not to prove it. If you just test specific examples, that doesn't count as a proof. But yeah. it can be helpful to check specific examples before you start to make sure that you're proving a true statement, and that if it's something you conjecture, that your conjecture is true. If it's something that you're given, that what you're trying to prove on a like test or something is like accurate. So, well, why might we care, right? Well, if you know the hockey stick identity, we can use this to prove that 1 cubed plus the 2 cubed plus, so the sum of the first n positive integers is n plus 1 squared over 2 squared. So this is also n plus 1 choose 2 squared. So maybe we'll just write this as 4. So, well, okay, let's see how, like, so 1 cubed is 1 plus 6, 1 choose 2, 3. 2 cubed equals 2 plus 6, 2 choose 2 plus 3. So on down to 3 cubed is 3 plus 6, 3 choose 2 plus 6. So we can continue like this until we get n cubed is n 6 n choose 2 plus 6 n choose 3. So now we add vertically. So by the hockey stick identity, so this is 1 choose 1, this is 2 choose 1, 3 is 3 choose 1, n is n choose 1. By the hockey stick identity, the sum of the first n positive integers is just n plus 1 choose 2. By hockey stick on the second column, the sum of all the n choose 2's is just, well, this is 6n plus 1 choose 3. And similarly, by hockey stick, this is 6n plus 1, or choose 4. So this will be accurate. So let's check. This is so we can factor out an n and n plus 1 from everything. We're left with this. Simplifying this stuff, get this. And finally, so 2 minus -4 is -2, plus 2 is 0. So this is n squared. -3n plus 4n is just n. We can factor n squared plus n. So this is and finally we get that this is exactly n squared plus 1 squared over 4, which is what we wanted to prove. So as an extra challenge, see if you can find a similar argument for n to the 4th, or n squared. So write n to the 4th as a linear combination of like n choose 1s, n choose 2s, n choose 3s, and n choose 4s. And then find a formula, sum the first n 4th powers, and then see if you can find an identity for the sum of like the first n positive 4th powers, or same for perfect squares. So by linear combination, I just mean some positive reals, or some reals a, b, c, d, so that n to the 4th is a times n1 plus b times n choose 2 plus c times n choose 3 plus d times n choose 4. And similarly, we can ask the same thing of n squared. In this way, we can find a formula for the sum of like I to the k for any positive integer k as I goes from 1 to n. So the sum of the first I k powers can always be determined using this method.